essentially, this problem was motivated when myself and a few others were trying to fine-tune these large language models to generate scientific hypotheses. And one key thing we noticed, which I'm sure anyone who's used Llama or Falcon or any of those sorts of models have noticed, is that it's really easy to get quite good output after fine-tuning, but that might come at the expense of diversity. So you generate a lot of really similar examples. Or conversely, you might be able to generate really diverse output, but you start to degenerate and get some really wacky stuff out the other side. So we sort of noticed this diversity coherency trade-off, and we wondered about how we could do things better, not in the fine-tuning process or with different architectures or anything like that, but at inference time, how can we reshape the probabilities that are coming out of these models so that they're more diverse, but they're also more coherent, they're more relevant to the task that you care about. So this was sort of a little like toy example, roughly what I'm speaking about. So we've all experimented with increasing the temperature and repetition penalties and all that sort of stuff. So imagine you're trying to generate scientific hypotheses for astronomy. Increasing the diversity, it gets good for a bit, but then eventually you start to get some pretty crazy stuff out the other side. Alternatively, if you want really authentic examples, in order to get really, really authentic stuff, you have to really turn down the diversity. And so if you trace out this curve, you sort of get this Pareto boundary of the best possible combinations of diversity and authenticity. And it's not very good. We want to move from points like A and B to C, which is a plausible scientific hypothesis, but it's still creative. It's not in the training set. And so the question, I guess, is how do we move from A and B to C? Is there a way we can do this at inference time? So this is sort of an empirical example. Nucleus, greedy, top K, they're all sampling methods. So when we're generating the next token, the language model outputs a probability distribution over tokens. These are simply just ways of selecting the next token. And as you can see, obviously, very context dependent on the hyperparameters, but as you tune those initially, you get improvements in both diversity and fidelity. But eventually we hit this point up in the top right-hand corner where the curves start to wrap back on themselves and we can't get any better performance. So what we want to do is we want a curve more like the red one where we can control it in such a way that we can keep improving both long past where these models start to wrap back on themselves and that trade-off kicks in. So there's some really similar ideas. So I mentioned nucleus and greedy decoding before. There's some things that are built on top of that. These are just other sampling methods that try and sort of address different aspects of this problem, perhaps in a more specific way. So classifier-free guidance simply looks at the probability of tokens with and without some additional prompt. So you might generate a probability distribution with the prompt, as we normally do, and then without. And then all they do is subtract the distribution without the prompt from the distribution with the prompt. And you can imagine that this increases the probability of tokens that adhere to the prompt better. And these other three methods are similar. So contrastive decoding subtracts the probability distribution from a really bad model, so maybe something like GPT-2, from a really good model, maybe like Falcon 40B. And there's a few other methods as well. And this can do many things. So classifier-free guidance can make you adhere to your system prompt, for instance, in ChatGPT, a lot better. Contrastive decoding, similar thing, can emphasize the really good aspects of the expert model and downweight the aspects of the amateur model that aren't as good, and similar sort of things for the other methods. So here, this is very similar to classifier-free guidance, it's just that you're truncating the context. So you're really emphasizing the start of the context when you subtract the probability distribution without that start of the context. And I guess a common theme here is that you can subtract and do really basic maths with these distributions in order to emphasize certain aspects of generation that you want and downweight certain aspects of generation that you don't want. So it's a really simple idea, but if you know what attributes you're aiming for and which models are going to give that to you and which models aren't, or even which bits of the prompt are going to give that to you, then you can do this subtraction. So that's the main idea behind what we're trying to do. So a lot of those methods we just mentioned, they perform one subtraction. So one is subtracting an amateur model from an expert model, or subtracting generation without the prompt from generation with the prompt. But since we're trying to beat this diversity coherency curve, the trade-off curve, we reasoned that we'd probably need to do two different kinds of subtraction. So I think the best way to think about this is to imagine some sort of real data distribution that we want to sample from. So for instance, the data distribution of scientific hypotheses. So we need an attractor in order to maintain coherency or fidelity or whatever you want to call it. So that attractor simply draws in examples, synthetic examples, into that real data distribution. So the idea here is really simple. It's called contrastive expert guidance. And we take our fine-tuned model, that's fine-tuned on scientific hypotheses, and subtract the logits from the same base model that's not fine-tuned. And in that way, hopefully, we're attracting these synthetic examples to the real data distribution. But obviously, if we turn up this attractor too much, we're just going to get a big clump of examples that may be really authentic, but remember, going back to that first curve, are not very diverse, like repeatedly asking whether the universe is expanding. So to counter this, we use a repeller. And this is another really simple idea. This time, we just feed in examples we've already generated, or even examples from the real data distribution, and append it onto the end of the prompt, and then subtract the logits that come out with those examples appended on. And it may not seem like that should work, but it does. So those examples become less likely to be generated again. So that's our repeller. It's pushing things away in the latent space. So these are the equations. I wouldn't worry too much about them, and feel free to talk to me about them after. But essentially, gamma controls how strong our attractor is, and eta controls how strong our repeller is. And if we can balance these two appropriately, then we have this perfectly balanced synthetic data distribution that aligns with the real data distribution. And if you set eta and gamma to 0 and do the maths, then all that comes out at the end is p theta, our original fine-tuned language model. So we just revert to our normal language modeling. And so this might just be a better way to visualize that. So up the top, we have our attractor. So subtracting p phi, which is our base model, from the probability, the logit distribution of p theta, which is our fine-tuned model. And then down the bottom, we have our negative prompting. So we feed in our C bar and downweight the generation of those same examples again, so that we're not generating the same things over and over. And again, if you control and balance the attractor and repeller perfectly, you start to align your synthetic examples completely with your real examples. So they're almost indistinguishable, and that's the aim. So a few results from our work. So we trained 3 different models, Falcon 7B for all of them, on 3 different data sets. So the first one was the archive hypotheses, so hundreds of thousands of archive papers, and we fine-tuned Falcon on that. The second 2 were toxic comment generation, and the last one was multiple choice question answering. And we used all these sort of synthetic metrics here to evaluate how good our synthetic data was. So normalized n-grams and diversity are 2 measures which measure diversity. And then the other ones sort of measure fidelity, so how closely is our real data distribution to our synthetic data distribution. And a lot of these are calculated with embeddings, for which we used the text ADA 2 model. And as we can see in almost every single category across all data sets, steer outperforms the other state-of-the-art sampling methods after we've hyperparameter tuned everything. And the important point to emphasize here is that these other sampling methods are also using the fine-tuned model. So it's a completely fair comparison. The only difference is how we're reshaping that logit distribution at inference time. So for the hypotheses, the best way we thought to supplement the synthetic metrics was to look at just whether humans prefer them. So we got 8 professors from ANU to evaluate the hypotheses. So here, these show the win rate against nucleus sampling, so what's considered to be the state of the art. And for certain values of eta and gamma, non-zero values, in particularly that bottom left-hand corner, we have a really statistically significant win rate over nucleus sampling. So our hypotheses are definitely preferred by people who know stuff about this. And GPT-4 was sort of similar. So we also had a look at the bit of a sensitivity analysis at how varying these parameters sort of affects how well they do in the diversity and the authenticity metrics respectively. And this sort of confirms what our intuition is. As we turn up the strength of the attractor, authenticity goes up. As we turn up the strength of the repeller, diversity goes up. And then somewhere in there is a sweet spot in which we can get really good performance. And yeah, just another way to show what happens as we vary each hyperparameter. Interestingly, for the number of negative samples, so when we negatively sample, we're randomly sampling from the real examples we've got and the synthetic examples we've already generated and append those onto the prompt. Interestingly, if you add too many in, performance really starts to go down, which is perhaps a bit counterintuitive, but I think that's mainly because the model starts getting confused and is trying to push itself out in a bunch of different directions at once. But yeah, there's definitely an increase when we go past 0 values of eta and gamma. They're perhaps not as prominent here because the other values aren't set to the optimal values at the time. But yeah, there's definite kicks in the curve. Another way to measure the synthetic data and how good it is training it on downstream tasks. So for the second 2 data sets, for the toxic and non-toxic comments and then the multiple choice QA, we can simply train a classifier on those and look at how well it does on the synthetic data. So for real data, a classifier trained on toxic and non-toxic comment embeddings achieves 98% accuracy. We got 94% with steer, which was significantly better than all other synthetic decoding methods. And same for the Q&A. We got significantly better results, sort of around 6% in some cases, for synthetic data trained, for a classifier trained on the synthetic data. So this is another probably key way to measure how good your synthetic data is. And yeah, finally just illustrating the trade-off. So this is sort of what we're talking about at the start. We really have pushed that Pareto curve outwards. We're beating the best hyperparameter-tuned nucleus and greedy methods, and for several different combinations of eta and gamma. This is perhaps not as rigorous, but I think this is a cool way to visualize what's going on. So if you embed the real and synthetic examples and then do dimensionality reduction, you can look at how the real and synthetic data sets align. And yeah, it's perhaps a bit hard to see with those small dots, but definitely with steer as compared to greedy, our distributions are much more aligned. And this sort of leads to the notion of perhaps like a convex hull precision and recall, so seeing how many synthetic examples are contained within your real convex hull, and then vice versa, how many real examples are contained within your synthetic convex hull. This is a bit hard when you reduce dimensions because obviously you lose a lot of interpretability and a lot of information, but steer seems to do quite well on this as well. Just one perhaps unfortunate result that we got was that we had both astronomy professors and other professors evaluate the results. They all knew something about astronomy, but the people whose primary degree was astronomy actually preferred the steer hypotheses less, so that's kind of suggesting that maybe in some ways this is gaming some of the synthetic metrics a little bit. So producing stuff that looks really good to us, but maybe not so in a really detailed academic context. And I think part of that is just how we set the task up. It's hard to state a really good hypothesis in one sentence, but that's something we're working on, looking into what's happening there. So I guess there's a few reasons why this is cool. It's definitely not going to like change the world or lead to GPT-5 or anything, but I think there's still a lot of good takeaways we can get out of this. So the first is if you're GPU poor, like I am, you can use it to sort of get a better boost in performance out of smaller models. So instead of trying to cram Falcon 180B onto your GPU, you can use a smaller model and then boost its performance by doing the subtractions that we talked about. The synthetic data sets, there's so much room for application there. At the moment, we're training it on essentially all of archive and looking to create a tool that will output really solid, like creative and also authentic scientific hypotheses, as well as solutions to those hypotheses. So I think there's many different applications that plenty of people could think of for applying something like this. And that sort of leads on to the next point, which is at the moment, most of the tools that we have to control how much diversity or authenticity we want is temperature and essentially prompt engineering, which is very much a dark art, and we've all spent a lot of time wasting a lot of time with prompt engineering. So this offers like a quantitative knob to tune, 2 knobs to tune, and if you can get the balance right, or even if you just want to tune one of the knobs, it just offers more fine-grained control over the outputs of your model. So you might imagine a legal team might really want to turn up the authenticity knob, but maybe an artist might want to turn up the diversity or creativity knob a bit more. And yeah, I think in the context of GPT-4, like obviously if you could fine-tune GPT-4, which we will be able to soon, it would probably outperform all the things we've got, and particularly if your real data set you're fine-tuning on is good, then it's going to push that Pareto curve out anyway. But I think there's still a lesson in here, or maybe just something to think about how we can offer a bit more control over these really big models, again, without prompt engineering. So imagine applying this to GPT-4 and being able to control that decoding method. And that's the great thing, is that the method is model agnostic. We can use it with sort of any sort of model we want. It's just applied at inference time and whacked on the top. There is a cool idea which I briefly wanted to mention because it came out after we'd sort of done most of this work, but it's a really similar idea, so we thought we were really clever and we're the first people to think of subtracting a base model from a fine-tuned model. Turns out other people were doing it as well, except what they did, they didn't subtract the logit distribution, so they didn't subtract the probabilities that come out at the end at inference. They actually subtracted the weights of the model themselves. So they took your fine-tuned model and your base model and just subtracted the weights. And I don't know if that necessarily should work again, but it turns out it did. And when you do the subtraction, you're simply just creating these vectors which emphasize the directions in the weight space where the models vary the most. And so there's a whole realm of applications there that you can think of, creating these things called task vectors. So taking the fine-tuned model and subtracting the base model and getting it to improve in one particular direction, but you can also do that many times and sort of add these vectors together. So doing things like learning via addition and task analogies. So I highly encourage people to check that paper out because it's really cool. And yeah, so sort of wrapping up, I guess I hope this provided a little bit of an insight into like how people are trying to control these models. There's definitely methods out there already, but I think we can hit on a more general method for navigating these trade-offs, and maybe even other trade-offs that we haven't really thought about. It doesn't have to just be diversity or authenticity. You control a lot of other aspects as well. And then on that point, like basically your control is determined by the type of subtraction you can come up with. So are you subtracting a fine-tuned model from an expert model? Are you subtracting generation with the prompt from generation without the prompt? So if you can come up with like clever ideas of subtraction, there's definitely a realm in which you can apply this to improve some attribute of the performance of your model. And another point was we found it really hard to synthetically evaluate these things, and I've had a lot of good conversations with people this morning about how they're trying to evaluate synthetic data. Basically, the best solution we have at the moment is to use human annotators, which is really expensive, and then maybe training like a reward model to copy what human annotators are doing, but we really don't have the best metrics for evaluating these things at the moment. So that's another challenge. And yeah, so wrapping up, I'd just like to thank my supervisor, Tang, and also the wonderful people at University TVD, particularly Maya for inviting me to the conference as well and letting me know about it. And yeah, thanks for listening.